Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the course Advanced Thermodynamics and Combustions. Today we are going to start module 7, that is Thermodynamics of Reactive Systems. So in this module we will cover two important lectures. First one is chemical and thermal analysis of reacting systems. Second one is simplified conservation of equations for reacting flows. So, we will start the first lecture, that is on this module, that is chemical and thermal analysis of reacting systems, lecture number 26, overall lecture number 26, and in this lecture we are going to touch upon the following topics, that is constant pressure fixed mass reactor, constant volume fixed mass reactor, steady state, steady flow perfectly mixed reactor and plug flow reactor. So, basically the entire idea or learning components for this module is the reacting systems. So, what does this mean is that in a combustion process the reactants vanishes, the products are formed. The conventional equations, thermodynamic equations based on mass, energy, entropy, all these equations are true as long as the system is in steady state or in a transient state. But on top of that, when you think about a reacting systems, in fact in a reacting system some of the species they form and some of the species also vanishes. Side by side there are some intermediate species, they are formed but they initiate the chain reactions, but subsequently when you look at the overall reactions they are not present. Another important segment is that the rate coefficients that generally governs the directionality of these chemical reactions also plays a crucial role. So, overall the chemical kinetics and the formation of different species plays an important role in the analysis of reacting systems. Now, to have such kind of systems in place, we are going to couple the governing equations of mass, energy and momentum equations with respect to chemical kinetics. That means, we will superimpose the chemical kinetics equation into this. So, this will give a complete overall picture of the reacting systems. With this viewpoint, four simplified models are framed, which are like constant pressure fixed mass, constant volume fixed mass, steady state steady flow and plug flow reactors. So, our entire intention will be to discuss some of the important aspects of these reacting systems. So, before we start, let us give some introduction to that. What do you mean by coupling reacting systems? If you look at the combustion situations, that is fuel mixes with oxidizer, it gives the combustion products, and with time if you look at the concentration of fuel, it keeps on decreasing, and the rate at which the combustion has products are formed, it depends on the global rate coefficient Kg, and the maximum temperature that can be achieved during a combustion process is defined through adiabatic flame temperatures, and these adiabatic conditions can be ascertained by assuming a constant pressure model or constant volume model. So, through this process we can say that when you define these adiabatic flame temperatures, we say that there is no enthalpy of combustion term. So, basically difference between enthalpy of reactants and products, they should equalize. When did they equalize? The equilibrium temperature, what is says is that adiabatic flame temperatures. Now, when we model such kind of systems, until this point of time when we have modeled this kind of systems, it all depends on the equilibrium conditions, that is reactants where they stand, products where they stand. That means all the thermodynamic parameters are estimated based on the reactant operating conditions or in terms of pressure and temperature, or product conditions in terms of pressure and temperatures, and we really do not bother how the chemical reaction proceeds. But the chemical reaction proceeds through chemical kinetics mechanisms, formation of different species like elementary reactions, formation of radicals through another elementary reactions, all those things. So, when you deal with a coupled systems, we try to mix both chemical kinetics as well as the conservation of principles, and by conservation principle we mean mass, energy. So, when we couple them, then we can say that the detailed evolution for this entire combustion phenomena can be formulated. So, with the knowledge of chemical kinetics coupled through the conservation of principle allows us for detailed evolution of the systems from its initial reactant state to the final product state, which may or may not be in chemical equilibrium. So, in other words, we can say system temperature, various species concentrations has to be obtained with respect to time as the systems proceeds from reactants to products. Of course, this reaction time scale is a very short duration events, and we can say it is something like in millisecond durations, and in these durations many species are formed and many species also vanishes. So, the chemical kinetics through estimation of rate coefficient will allow us to model such kind of simulations when you go from reactants to products. Now, to do that, there are two approaches that one can design. In the first one or the first analysis, the thermodynamic system is considered without complications of mass diffusion. So, mass diffusion is a term where the a species diffuses into other and through this mass diffusion does not arise in this case. That means, in our conservation equations we will not look into the mass diffusion terms. The second part of the analysis will cover some of the preliminary mass diffusion effects into the chemical reactions. So, for the simplicity we will now consider the first part where the thermodynamic systems is analyzed without mass diffusion. There are four models that are possible. First one is constant pressure fixed mass reactor. So, it is a perfectly mixed homogeneous reactor. So, as you see in this picture, so it is a constant pressure. So, we have a piston cylinder, and this particular system is viewed in this manner. So, we have a thermodynamically we can say the fixed mass reactor is modeled by putting a certain mass onto a piston, and entire system or gaseous medium is within this cylinder, that is reactants as well as the products, and this mass allows us that piston does not move. That means a fixed mass is experienced by these species, and since all these species and these reactants and products in this domain, they are perfectly mixed and homogeneous. Other type of situation can be modeled, that instead of fixed mass we can ascertain that we have a fixed volume systems, but in these fixed volume systems the pressure can vary with time. So as the reactions evolution starts, the pressure can vary with time. But when we say fixed constant pressure reactor, volume can change but mass remains same. Another model is that well stirred reactor. So when you deal with the constant pressure or constant volume reactor, we try to see how temperature changes with time, how concentration changes with time, and in a constant pressure reactor we see that how volume changes with time, and in a constant volume reactor we have same things like temperature and concentration that changes with time, but at the same time we look into how pressure changes with time. But in a well stirred reactors we assume that all these things, that mean temperature is always constant, concentration is constant, pressure is also constant. But what happens is that it's a steady state, steady flow analysis, and in a perfectly mixed. Another kind of reaction is a plug flow reactors, that is a steady state, steady flow, but no axial mixings. So basically this is a kind of a duct in which certain gas is passing. So something like in a aerospace propulsion system like ramjet in combustion or scramjet combustion, some high speed air that enters and fuel is injected into it. So it's a completely so we can say that we can arrest the flow, I mean mixing in one particular directions. So like in a plug flow reactor we can model this as a steady state, steady flow, but we do not allow any kind of axial mixing. There is no axial mixing, but there can be lateral mixing. Now out of all these four model we will analyze one by one, but we will give more emphasis to the first model, and other models will just give the some glimpses that how they are modeled. So in the first model what we see is that it is a constant pressure fixed mass reactor. So we consider the case in which reactants are contained in a piston cylinder arrangement, and when they react and at each and every location within the gas volume at same rate. That means reaction takes place in this entire space at same rate. That means every mass or every species sees similar reaction coefficients or kinetics at in all at every locations. Since there is no change in the temperature or composition gradient within the mixture, a single temperature and set of specific concentration is sufficient to describe the evolution of the systems. Now if you say that the reaction is exothermic, then both temperature and volume will increase, and with time, and there may be heat transfer through the reaction vessel as well. Now our objective is that how we want to model this temperature, volume or species evolutions when the reaction proceeds. So towards the end of the things we will see that we need to find some differential equations and those equations can be modeled through initial value problem. That means with the initial conditions they can be modeled. Now let us understand the basic mathematical concept behind the fixed mass constant pressure fixed mass reactor. The first thing that we are going to analyze is the how temperature evolution takes place during the reactions. So, we consider that basically we are looking at temperature, concentration and volume, how they changes with time when the reaction proceeds. So, first equation that we recall is the first conservation of energy from the first law, but here we are looking at this energy equation in the rate form. Rate form means we are looking in terms of time. So, that is what rate equations are expressed, q dot minus w dot is equal to m into du by dt. And here u term we express in the form of enthalpy. That means, we know H is equal to u plus Pv. From there we can frame an equation du by dt is equal to dH by dt minus P dV by dt minus V dP by dt. Now, when we have these equations, also the work term that can be expressed in the form of pressure P dV equations. So, W dot by M you can write P dV by dt. Now, putting these two terms in these equations, we can say the main equation takes in this form, where we can say W dot by M and P dV term they vanishes, they gets cancelled from the both sides, and since it is a constant pressure reactor, we can say dP by dt term goes to 0, then q dot by m takes the form dH by dt. Now, then we need to find out what is this dH by dt. So, for that to do that, we recall this system enthalpy H, specific enthalpy in terms of H by m, and in terms of molar form, because all our analysis has to be done per mole of the fuel. So, we can write this total enthalpy as Ni Hi bar for all the species I is equal to 1 to n divided by m. So, then we can find out what is dH by dt from these equations, and if you can see that the each species are formed, its enthalpy is also changes with time, and time because the temperature also changes with time. So, these two terms are function of time and they are related. So, this differentiation can take place in the manner that we can say dH by dt is equal to 1 by m summation of Hi bar dNi by dt plus again summation Ni dHi by dt. Here we are now going to take some approximations. Till this point of time we have been considering the ideal gas behavior for these mixing systems. So, we can say, if you when you say ideal gas behavior, enthalpy is a function of temperature only, and that also can be represented in terms of Cp dt, where here it is a constant pressure. So, I write molar specific heat for species I. So, this is one part. Second part, we can also recall the system compositions. Now, try to look into the number of moles of species that is formed, and which is nothing but the concentration of respective species multiplied by its volume. So, from these equations we can find out how the number of moles for any species I changes with time, and this is nothing but dNi by dt. Now, we write it as V into omega dot I, and omega dot I is nothing but concentration of species change with respect to time. So, putting all these terms in this q by m there, q by m is dH by dt, and from this dH by dt and in this dH by dt expression is here, and here we have Hi term, we have dHi term, then we have Ni term, and we have dNi by dt term. Putting all these things, we are now in a position that after simplifications we frame the expression rate of change of temperature change with respect to time, and which is nothing but a ratio in which the numerator is equal to q dot by V minus summation of hi omega I divided by summation of I concentrated xi into Cpi. So, here we have to recall our previous concepts how to find out hi. So, hi is nothing but the molar specific heat for species I, and it has to be calculated from its enthalpy of formation value through Cp times T. Cp is also changing with time, and the volume also we can express in terms of mass, concentration and molecular weight. So, by putting this, we are in a position that we can find an equations in which we can write how the temperature of the reaction changes with respect to time. In a similar analogy, we can also derive another expressions how species evolution takes place during an reactions. So, here we start with is a concentration of species I dxi by dt. This concentration can be expressed in terms of number of moles by total volume. Then we can differentiate. After differentiation, we arrive at this expression dxi by dt is equal to omega I minus concentration of xi 1 by V dV by dt. So, means that same concentration of species I changes by two terms. One is the rate at which it is formed, and other is the due to the concentration change with respect to volume. Then further we can write this system equations Ni, and we can also make ideal gas expressions to and when you do that we can rewrite this particular equations in this manner. That means, we can find from this equation what is 1 by V dV by dt is equal to 1 minus summation of Ni summation of dNi by dt plus 1 by T dt by dt. Okay. So, when this equation and this equation when this expressions is used in this concentration term, we arrive at another expression, that means how concentration of species I changes with time. So, if you look at these two equations in the and try to correlate what we are trying to achieve, we are trying to achieve how temperature changes with the time, which we get from this expression. Second one, we are trying to see how the concentration changes with time, which we can achieve through this, and we also see how volume changes with time, this we also can achieve with time, achieve from these equations. So, we have all these three equations which are needs to be solved simultaneously. Now, to carry out these equations, we require some initial conditions, and at initial conditions you can assume some initial temperature T0 at temperature at T is equal to time is equal to 0. What is this initial value? Concentration at time is equal to 0 at what is its initial value. Okay. Now, the solution for this problem requires this new equation is to be solved along with the reaction kinetics to find the we need to program this, or we need to do some kind of programming which can be coupled with respect to chemical kinetic reactions to solve these equations. We are not going further deep into it because it is a completely different research problems and which are not proper in the purview of this course. Then we will move on to the constant volume fixed mass reactor. Here we are looking at the situation that reaction is taking place in a container which is a fixed volume, and we are trying to see how temperature and concentration of species changes with time. At the same time, we also look at how pressure within the container changes with time. But only difference between the constant mass and constant constant volume and constant pressure reactor is that in a constant volume reactor follows closely with constant pressure, but only with the absence of work, because there is no PdV work is involved here. But side by side another important point is that when you look at the constant volume reactor, pressure changes with the time. So, it may so happen that when the reaction takes place and suddenly we do not take care the materials of this in which the reactions is taking place, then it can explode. That means, if the pressure changes with time and it is such that the material is unable to withstand that pressure, in such cases it can explode. So, for such analysis, variation of pressure with respect to time is also equally important. And again it is an initial value problem which can be coupled with reaction kinetics for the solutions. So, here we recall the same equations, q dot by m is equal to du by dt, and here since it is a constant volume situations, we can recall the internal energy and enthalpy can be related through an ideal gas equations. Also we have Cp and Cv relation in terms of its universal gas constant characteristics gas constants, and the expression for dT by dt is, or evolution or derivations for dT by dt same as that of constant pressure reactor, but only difference is that in the expressions instead of molar enthalpy we have used molar internal energy here. Again we instead of specific heat at constant pressure we have used here specific heat at constant volume. With this only changes one can write the equations dT by dt in this form, and since we know that this internal energy or enthalpy are also related, so another equations can be framed by including enthalpy terms here. Then now again in this equation also we can look into how the concentration of species I changes. So, this equation can be integrated simultaneously with rate expressions to find two complete expressions, that is temperature change with respect to time, concentration change with respect to time. With same initial conditions and reaction kinetics, the systems can be modeled with respect to ideal gas frame of equations and system compositions. So, ultimately there are two equations that needs to be solved, dT by dt and dxi by dt with these initial conditions and chemical kinetics. Other equations that you require, how pressure changes with time, which we get from an ideal equations dP by dt, and which is nothing but the function of this concentration and omega I bar. Omega I bar is nothing but the change of concentration with respect to time. Okay. So, so this is how you are going to solve. Again the analysis we are not going deep into that, but to have some kind of philosophy or glimpses, an example or solutions for by solving a constant volume mass reactor, one can achieve some analysis. If you look at this particular plot, it shows the how the reaction evolves when in a IC engine, and in particular it is an SI engines, to predict the temperature, concentration history, rate of pressure rise, knocking behavior for ethane air mixture. So, you might be knowing about trends of the plots much earlier in the IC engine course in the thermodynamics, but where we see is that when you look at those things, those are major data, and during the engine running operations we can get how the reaction or they are basically experimental data which were acquired during the engine operations. But what we see here is the model data, and in this model data the fuel that is taken is ethane, and it is getting combusted in the air, and when it is utilized in an SI engine, you can see let us see for the fuel with time its concentration suddenly drops up maybe after 3 milliseconds. If you look at the products that are formed, its concentration keeps on increasing with time, and so on. So, this is the reactants, and when it fuel gets oxidized, products are formed, and through these things initially the temperatures that is there, it suddenly rises. Once rises after all these things occurs after 3 milliseconds. So, this is the what you say temperature rise. Now, if you look at rate of pressure rise, pressure initially you can see there is a steep rise in the pressure close to about after 3 milliseconds, and it goes on, and you can have a peak pressure at some point, some of the point instantly. So, you can say it is instantaneous pressure. Now, if this pressure is coupled with subsequent operations, you can see some situations if your fuels and air are not adequate, combustion takes place in an adequate manner, we can see the unexpected rise in the pressures with time. So, this is something like knocking behavior. So, what the significance of these plots is that all these parameters are modeled in a through this constant volume fixed reactor scheme, and with this we are trying to predict the different fuel and product concentration as well as the pressure changes with time. The next reactor that we are going to analyze is a well-started reactor. So, till this point of time it is we are looking at how the reaction takes place with respect to time. So, but in a well-started reactor it is a steady state, steady flow, perfectly mixed reactor. We can imagine that some fuel is entering continuously, and the mixing takes place in one things, and products are leaving. So, after reaction the products are leaving, and in this entire model the temperature remains constant, concentration remains constant, and pressure remains constant. But what changes is that within this control volume we are looking at the mole fractions, temperature, pressure and volume, or we can say what is this steady state value. When something is coming, that means in the inlet we have certain mass flow rate, mole fractions, its enthalpy. Outlet also you have mass flow rate, mole fraction of species and enthalpy. So, it is considered an ideal reactor in which perfect mixing is achieved inside the control volume, and it is mainly used to obtain the values of global reaction parameters. So, basically it is a when it is modeled, it is modeled with the rate chemical kinetics of global reactions, not for the elementary reactions. That means, we are not bothered about the elementary species formations. So, typically this kind of reactors are employed for NOx formation, to study the NOx formation behavior, flame stabilizations, and here we are looking at the mass conservation of individual species. So, how do you do that? To do that, we can say that we have to analyze the overall continuity equations in terms of mass generation terms, because chemical reaction transfers from one species to other. The positive generation rate, that means within this control volume, the positive generation rates indicates the formation of species, and the negative generation rate indicates that species are destroyed. And in our combustion term, the generator terms are referred as source or sinks. Source means it is formed, and destroyed means it is a sink. So, it goes to the sink, and to do this analysis we need to frame appropriate form of equations for each species. There may be n number of species. The well-stirred reactor assumes steady state, steady flow for which time derivatives expressions disappears. So, how does it look like? We can see here that the outlet mass fraction is equal to mass fractions within the reactor. Since the compositions of the reactor is same everywhere, composition of the outlet of the control volume is same as that of interior. So, through these equations one can write mass conservation of arbitrary species. We can write this rate at which the concentration of mass changes with time has three terms. One is, that is, rate at which mass accumulates in the control volume is dmci by dt, the first term. The right hand side first term refers, that is, mi dot triple dot v is the rate at which mass of I is generated in the control volume, that means some species are generated. M dot I in and M dot I normally refers to the inlet and exit conditions. The mass flow rate I into the control volume and out of the control volume. Now, this first term M dot I triple dash is nothing, can be correlated in terms of its molecular weight and the concentration of rate of change of concentration of species omega dot I. Okay. And this can be written in the functional form, and that can be written for inlet as well as outlet. And M dot I we can find its the total mass into its mole fractions. M dot I we can find out what is M dot I out into its mole fraction, Y dot I out. So, putting these equations, and here we, since it is a steady state situation, this term vanishes, that means it has to be 0. So, from these equations we arrive at this expression omega I dot is equal to into molecular weight of species I into volume plus m dot into y dot I in minus y dot I is equal to 0, and this relations m dot omega dot I and y dot I can be expressed in this manner. Then moving further, we can also find another equations which is the conservation of energy, involving what is the enthalpy which is going out and what is the enthalpy which is coming in. So, difference in of this enthalpy multiplied with mass will give you the energy conservation equations for each species. So, we have energy conservations, we have mass conservations. So, both the equations can be solved simultaneously with for species fractions and product composition constant by the through chemical kinetics. And another important term which is normally defined in a well-stirred reactor is the mean residence time for the gases. So, it is nothing but we say that during this, as the reaction proceeds, certain gases for the subsequent reactions to allow, there is some residence time for each gases that remains at one particular time. So, that is called as mean residence time for the reactor in the gases. So, that is defined as TR, it is rho times B divided by m dot, and rho is nothing but the density of the mixture, and this can be calculated from the ideal gas relations by knowing the molecular weight of the mixture. Okay. So, the well-stirred reactor is assumed to be operating at steady state, which means there is no time dependence on the mathematical models. So, equations describing the reactor are a set of non-linear algebraic equations in the form of species and temperatures. These are nothing but the algebraic equations. So, now next reactor which we are going to analyze is a plug flow reactor. The plug flow reactor is another kind of reactor in which we see that the reaction proceeds as and when the flow is happening. You can say that the flow is going from one directions, that means there is one is direction of the flow is fixed. Either this flow can be mixture of both reactants as well as products, or it can be a situation that the air is entering and fuel is being spread into this medium. So, such kind of situations are modeled through plug flow reactors. But what assumption it says that temperature, it says that the temperature, pressure, those things and concentrations, they vary only in one particular direction. Of course, there is velocity that varies with one particular directions, and there is no axial mixing. So, it is a steady flow, so there is no time term, it is a steady flow, steady state, steady flow, but no axial mixing. So, the plug flow reactor represents one of the ideal reactor which has following attributes. It involves steady state, steady flow, one dimensional behavior, there is no mixing in the axial directions, which implies that molecular and turbulent mass diffusion is negligible. The properties are uniform in the direction of the flow. So, thus a single values of velocity, temperature and composition allows completely to characterize the flow. It is an ideal frictionless flow. So, that means we can use Euler equations to describe pressure and velocity. One can assume an ideal gas behavior which allows the steady state equations. So, we can say it is a similar to that of a constant pressure or constant volume models expressed in a spatial coordinates rather than time coordinates. So, I am not going to go deep into details, but just to see that how the four governing equations are modeled. One is mass equations. So, we can say there is a flow, we can assume some elementary length dx, and across that length we can find a control volume. Within that control volume we are trying to see what is the fluxes that entering and what is the fluxes are that leaving. Now, when it is entering, how much force it carries, how much energy it carries, and this and how many species it contains. So, all these things can be equated. Now, when you equated, there we can find four different equations. One is mass conservation, momentum conservation, energy conservation and species conservations. And by doing so, we can solve for two important equations, what is d rho by dx and what is dt by dx and what is dy by dx. So, these three terms needs to be find out, and from this equation of course, if you see it is a big equations, but most of the things are known, and each equations can be drawn for individual species, and we can find out the density change, temperature change and mole fraction change with respect to time. And of course, here also another term that can be find out, what is the residence time for gases in the with respect to a particular locations. But one significant advantage that it contains the ordinary differential equations, and which can be solved with some certain initial conditions for its solutions. So, in summary, what I can say that all the reactions models what you have described so far are highly mathematical in natures, and there are many number of species, means number of reactions also will also be higher. So, if you are n number of species, the number of equations will be also n number of such equations, and each equations has to be linked with respect to its chemical kinetics form, so that to arrive its solutions. So, four models are explored: constant pressure, constant volume, Wells Tirade and plug flow reactor, and each of them has to be developed with conservation principle linked to chemical kinetics. Through this model, some of the characteristics of thermal explosion, that means can be explained related to reciprocating engines. We can also relate the information of how pressure changes with respect to time, so that we can formulate the expression for explosion. So, the understanding of the simple model will benefit the complex and rigorous analysis of combustion systems. So, we are not going to deep into these models, because it is not in the purview of this course, but however, the fundamental concepts of reaction models and its corresponding chemical kinetics will help for the learners, so that they can create their own combustion models for different chemical reactions. Now, before we proceed, I will just try to solve a very simple problem. We are trying to link this particular concept with a compression ignition engine combustion. What we are looking at in a CI engine combustion, we all know that in a CI engine combustions we have a diesel fuel and air, that mixing takes place in the combustion chamber. In a compressed air medium, the fuel is sprayed. So, we can assume that as if some of the fuel is entering into a combustion model, and we can assume this combustion chamber as a control volume. So, we can here we say, and if you look at these things, these are different mole fractions, temperature, pressure and volume, which changes with time, pressure and volume, and it is a steady state reactor. And here we are seeing that we have fixed air, or we say it is a compressed air, and fuel is entering into it, and in this case it is diesel, and its Ceten number is given as 41, and out of this we have some combustion products. So, there are many models that has been derived. So, in a diesel engine combustion, we all know there is a term called as ignition delay. Ignition delay is like at certain time fuel is injected, but the combustion happens after some time, after certain period of time, and this ignition delay is correlated with respect to UP bar, that is average piston speed, activation energy, universal gas constant, initial temperature, compression ratio, initial pressure. We need to, and this is a semi empirical relations, and with this engine data we are expected to find what is the ignition delay period. So, of course, the problem is simple and all the data are given, but only thing is that we need to meticulously find out the different parameters which are appearing in these equations. So, in these equations what parameter is required is UP bar, average piston speed, which needs to be calculated, EA needs to be calculated from this equation with the value of Ceten number. All other data are given. So, data that are given as PI is 0. That is initial pressure is 0.98 bar, that is charge is entering. TI is 40 degree centigrades, and this number has to be in Kelvin, 314 Kelvin. RC, that is compression ratio 16.5, R bar, that is universal gas constant 8.314 kilojoule per kg mole Kelvin. So, these data are given. What we do not know is what is EA and what is UP bar. Now, to calculate this UP bar, other engine data is given. What is that? Total number of cylinder is 6, total displacement is 15.6 liter. So, we can say total volume V is equal to 15.6 liter, that is 0.0156 meter cube, and total volume is nothing but number of cylinders into pi by 4 B square, that is bore, into stroke, that is equal to 0.0156. Now, B we can say bore and stroke relations is this. So, we say stroke is equal to 2.02 times bore and number of cylinders is 6. So, by putting this we can say 6 into pi by 4 B square into 2.02 B, that is equal to 0.0156. So, this equation will give you the value of B as 0.118 meter and stroke is equal to 0.238 meter. This UP bar is nothing but twice times S into N. So, this is the term average piston speed, and that two terms comes because it is a 4-stroke engine, that is 2 revolutions, 2 power stroke. So, 2 into S into N, and when you put this we can say UP bar value as 7.8 meter per seconds. So, we are now able to find UP bar. Then other term that needs to be found, what is EA, activation energy. Activation energy is related with another activation energy for the fuel, that means during the reactions when the fuel is that which is carrying the energy which is during the reactions, the chemical bonds needs to be broken. As a result, the energy which is going to be released is through its activation energy due to chemical bond. So, this number we can find 618,840 divided by Sitten number. Sitten number is 41 plus 25. So, this empirical relation we say is 9376 kilojoule per kilomole. So, in this equation all the number are known. So, by inserting values one can find out ignition delay in terms of degree crank angle. This is 3.9 degree. So, ignition delay can be expressed in terms of two things. One is in terms of engine viewpoint, we express at what particular locations the fuel needs to be injected and at what point the combustion takes place. So, this is represented in terms of degree crank angle. Now, in terms of time, this can be converted by knowing engine speed. Engine speed is 980 rpm. Now, to do that, the relation that we can say ignition delay in the seconds, we can write ignition delay in terms of degree crank angle divided by rpm, that is 980 by 60, this many revolution per second, and each revolution means 360 degree per revolution. So, revolution gets cancelled, degree gets cancelled. So, this number now becomes 3.9 into 60 divided by 980 into 360. and then this becomes 0.00066 second, and so ideally the ignition delay can be approximated as 0.66 millisecond. So, in a when such a model is done for a fuel, we can say the ignition delay that defines the time at which fuel is ignited, and at the time difference between the time of injection and the time of combustions, and in this case it is 0.66 milliseconds. So, with this I conclude. Thank you for your attention.